So now we're in section 4.2, which is talking about area. So we talked about antiderivatives last time, the opposite of derivatives. Now we're switching gears, talking about area. We'll see how they come together later, maybe. So before we even talk about area, actually, we have to talk about sigma notation, which you might remember from series. But let's just talk about what it means first on example 1. So what it means. Notice that we have I, and then we have I equals 1, and then we have 6. So what this is the I in the middle is a formula to calculate the next term, to calculate each term. And then the I equals 1 is telling us where we start. So we're going to start with I equals 1, and we're going to go until I equals 6. And so in this case, it's pretty easy because the formula is just I. So that just means we're doing when I is 1, it's just 1. When I is 2, it's just 2. And then the sigma means we're going to add all these together. And we're just going to go up until I equals 6. And so what is that? That's 7 times 3. So that's 21. And then the next one is a similar idea. I actually think we're going to get the same answer. But look how they just did this a bit differently. So here they're starting with I equals 0, but your formula is I plus 1. So that means at first, when I equals 0, to get your first number, it's 0 plus 1. So your first number is still just 1. When I equals 1, it's 1 plus 1, which is 2. When I equals 2, it's 3. When I equals 4, it's 5. Wait, was I saying that wrong? When I equals 0, it's 1. When I equals 1, it's 2. When it's 2, it's 3. When it's 3, it's 4. This is when it's 4, it's 5. And then when it's 5, it's 6. And you see 5 is the biggest thing I should be. So this is representing 1 plus 2 plus 3 plus 4 plus 5 plus 6, which is again 21. All right, so now it gets a little more interesting. So look at what it is here. Here, notice they use a different letter. That's fine. Whatever letter you use doesn't actually matter. So they use J. And here the formula is J squared. But we're going to start here when J equals 3. So the first one is 3 squared, which is 9. And then when J equals 4, 4 squared is 16. When J equals 5, 5 squared is 25. When J equals 6, 6 squared is 36. And when J equals 7, 7 squared is 49. And you see that's where we stop. We stop when J equals 7. And so there we go. We just got to add those together. So try to do it intelligently. 9 and 16 is 25. 25 and 25 is 50. And then over here, add the 1 to this. Make it 35 plus 50. So that's 85. So altogether, it's 135. And let's see, just to be clear, because we went a little faster with our mental math, and just to show as an example, Desmos can do these. So you can type in, I think you can type in sum or sigma, but you can also go to here to get the functions. And so we'll just use n, or no, we'll do what they do. So they use j. So j, we'll start off at 3. We'll end off at 7. And our formula will be j squared. There we go, 135. So just to show that Desmos can do those as well. So what are we going to do here? You go from k equals 1 up to k equals n. So that's an infinite series thing, isn't it? Do we need to maybe break out some formulas here? Or let's see what's going to happen, though. So well, let's talk about this. So if you've got this 1 over n here, we can pull that out to the front, right? Or let's not do that first. Let's write it out as how it is. It's just weird because it's not going to be able to come out very nice. So this is k equals 1. So this is 1 squared plus 1. So that's 2. And then you add, again, the 1 over n. When k equals 2, 2 squared plus 1 is 5. So times 5. And then again the 1 over n. And that's when k equals 3. 3 squared plus 1 is 10. And then we have to keep doing that all the way up to 1 over n times n squared plus 1. So I don't know if the textbook wants us to use a formula or wants us to just be thinking about it like that. Let's take a look real quick and see what they're saying here. Right, so they wrote pretty much exactly what we did. They're just trying to think about it as an infinite series. Or not infinite, but up until where it ends, which is when k equals n. Okay, so we're going to have the same thing here. So, let's see, delta x, that's just like its own variable. They're trying to get us to look ahead here. But notice there's no I, so that delta x is just the same. So this first one is going to be f of x sub 1, because see, that's where the I is. So that just means that like x is a set, and that's going to like the first term. That's pretty much what that means, is like the first one. And then the next one when I equals 2, so that's going to be f of the second x value. Dot, 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 all the way up to the nth. Now, I think this looks kind of confusing. I wouldn't worry about this too much. This is trying to just look ahead to some other formula. And that formula in itself, I don't really like to think about, because I like to think about just what's actually happening anyway. But I suppose you should be able to see. You just look at how each one, we just have that same formula. All that changes is that I. It goes from 1 to 2 to 3 to 4, all the way up to n. So that's like, yeah, that's what summation notation means. But then we have these formulas as well that allow us to simplify some stuff. So let's think about some of these formulas for a bit. So this first one here, if we just looked at this, what would this even mean? Well, what is the formula? The formula is just a number. Notice how there's no I involved even in there. So this just means that's what it is when I equals 1. This is what it is when I equals 2. This is what it is when I equals 3. No matter what I is, it's just always C. But you're still doing it for how many I times there are. You're still doing that in times. You still have that many terms. So what you're doing then is you're just adding C to itself in times. That's why it's C times n. Now this one, number 2, do we know how to prove this one? Yeah, actually, I do know how to prove this one. So look at what we have going here. If we would write this out, we'd have 1 when I equals 1, when I equals 2, when I equals 3, when I equals 4, all the way out to when I equals n. Right. So the idea here is what I actually showed in the other one, is that if we did all this out, all of these numbers would add to the same thing. They'd all add to n plus 1. So when I think about these pairs, the pairs add up to n plus 1. Notice how I wrote that up here. There were 6 of them. The pairs added up to 7. But then the idea is, how many pairs are there? Well, up here, there were 6 numbers, and there were 3 pairs. So doesn't that make sense? If we want to find how many pairs there are, we're going to take the total amount of numbers and divide by 2. So we're multiplying that by the total number of numbers divided by 2. And look, that's exactly what this formula is right here. So, I mean, that's two proofs right there. Two proofs of those two top formulas. Formulas 3 and 4, we're not going to prove right now. Maybe we'll prove them later. I mean, the honest truth is I don't know the proof off the top of my head. So maybe we'll prove them later. But for now, we'll just use them. And we're going to use them to break this down. So let's see. Another thing that they didn't talk about here. Well, I guess they did talk about that. That's with the constant. So let's see. What do we have here? Let's rewrite this. This is the sum of I equals 1 of n. Oh, should I just hard it too? So let's hard it. I over n squared plus 1 over n squared. And I suppose they don't show it up here as a formula, but this is a formula we could know, that if we have this of a plus b, you can separate that into two different sums. Why can you do that? Well, because this is just sums in the first place. So like over here, you're just going to have a plus b plus a plus b plus a plus b plus a plus b. So why not just reorganize that to a plus a plus a plus b plus b plus b? So that's a formula that we know. And that's what we're going to use down here. So we've got the sum of I equals 1 to the n of I over n squared plus the sum from I equals 1 to n of 1 over n squared. And now, what do we do? Well, this over here is, or not the whole thing I guess we should look at. We should just look at this. That's a constant, right? That's just a plain number because there's no I involved. So right there, we can apply this number 1 formula right here. That if we have the sum of a constant up to n, it's just that constant times n. So this sum right here is going to be that constant, 1 over n squared, times n, which is going to cancel out to be just 1 over n. And then the next one, so we have a constant times I. So just like we had up here, I didn't really point it out, but notice we had that 1 over n, and I almost said that we could factor it out to the outside. And that's true, because notice how with this out here that I wrote, we could factor out an n if we wanted to. So that makes sense, that because this is just adding things together, if there's a constant, a coefficient on the inside, we can pull that out to the front. And why is that different than what we did here? I just want to clear that up for myself. So from here, if we wanted, we could have pulled that out to the front, right? And that would just leave us with a 1 on the inside. And then if we applied the same sigma formula, it would just be 1 times n times the n squared. So it's actually the same thing. Okay, so that's why it might seem a little different than what we did here, but it's really the same kind of idea. So I'm going to do that idea here. I'm going to go ahead and write it out. Bring out the 1 over n squared, because then that just leaves I on the inside. And so now we can apply this formula number 2, where the sigma of I is n times n plus 1 over 2. But that's multiplied by n squared. Okay, so now the n's cancel. We have n plus 1 over 2n plus 1 over n, which means I just need to make that a common denominator with the 2 to say that this is n plus 3 over 2n. So this is equal to this. This is equal to n plus 3 over 2n. At least that's what we got. Because the whole idea is now that we have that nicer formula, we won't have to write all of this stuff out. Now we just have a formula we can easily plug in n for. So we plug in 10, we get 13 over 20. You plug in 100, you get 103 over 200. You plug in 1,000, 1,003 over 2,000. And you see what's happening here. This is definitely approaching 1/2. I don't know if that means anything or not. But that's pretty nice. Now that we have that, we just get something we can go ahead and plug it right in. Let's look at Desmos and see if that's true. Just because Desmos can provide some interesting stuff here. So let's again do a sigma. Let's just type out the whole thing. Then we'll even add sliders. So let's go ahead and name it how they do so we don't get confused there. So I equals 1 up to n. Or you know what I want to do it? I actually don't want to use an n. I want to use an x. X. And then open parentheses I plus 1 close parentheses divided by x squared. Okay. So that's a little concerning that there's no way this is going to look exactly the same because of the weird jumps and stuff. Maybe that's okay. So x plus 3 divided by 2x. Oh, yeah, no. Look at how that's going to be right on for the integers. Yeah, that's going to be perfect. Because the whole point is we want to be able to say, if this is f of x, that's one function. Call this g of x. That's the other function. And then we'll do this. We'll go, what is f of n? We'll go, what is g of n? And then we already did, add a slider for n. And the idea is those should be the same. Not whenever n is an integer, they should be the same. So let's make sure it worked out. So when n equals 10, they are indeed the same. Is that 13 over 20? Yes, it is. If n equals 100, are they the same? Indeed they are. If n equals 1,000, are they the same? Indeed they are. If n equals 10,000, are they the same? Indeed they are. And should we just make sure that that is 10,000 divided by 20,000? Right, we don't need to do that because, for one, we're going to mess up if we try to do that, and that's just how we program the formula. So that's showing that they are always the same, at least for the integers, because the integers are all that apply for a summation in reality. Okay. So the whole reason we're doing this is because I think, in the next problem, we're going to make a summation based on what they tell us here. And then we could think about taking that to infinity. They don't want us to do that in this problem. We could try that anyway, though. So let's see what we're trying to do here. So we've got our function. Let's graph our function. So we know for sure. And it's negative x squared plus 5. So we should know what that looks like. It's going to be up 5. And then it's going to have these points going down. I want it to be perfect. So it's going to be like that. Let it pop. Or not. Let it pop. What? There. And that's there. There we go. So there's our parabola. They want us to find the area in between 0 and 2. Oh, use the 5 rectangles in the picture they give us. Okay, well, let's look at the picture they give us. Ah, okay. Let's take this picture. We can explain a lot through this picture. So here's what's happening. Notice they have their parabola. That's their parabola, their black line. So they're looking from 0 to 2. That's why it doesn't go to the end, just like ours doesn't go to the end. And they're trying to they're saying this is an overestimate and an underestimate. Because look at how when we calculate them like this, where the rectangles are on the right side of the graph, or the right side of the rectangles are on the graph, then we're missing all of this area. So what we're getting is an underestimate of the area. But if we look at them like this, what we're getting is an overestimate of the area, if all the dots are on the left side of the rectangles. Or at least in this case. So what they wanted us to do here was look and actually calculate the area of these rectangles, because that's not that bad, right? Like, the area of these rectangles, it's really just looking at them. So I would look at these rectangles, and let's do the underestimate first. So I'd say, like, the width of this rectangle is 2/5. Because the area of a rectangle is just base times height. Like the width times the height. So 2/5 is the width. And then what is the height? Well, it looks like the height is whatever that height is. So what is that height? How do you get that y value? Well, notice that that is just a point on the graph when x equals 2/5. So to get the y value, that's just f of 2/5. Because that's the height of the rectangle there. So the width is 2/5. The height is f of 2/5. And look at how we keep going. Well, the next rectangle, the width is still the 2/5. The height is 4/5. Or f of 4/5. Because now we're here. This is the point that we're trying to find to get the height of the rectangle. F of 4/5. And I think what they want us to do is just add all these together. So let's start and then continue out the pattern. So what is f of 2/5? We do have to calculate that. So f of 2/5 is negative 4/25 plus 5. Okay, that's going to get crazy fast. Because that's 5 times 25 is 125 minus 4. So 121 over 25. So that first one is... Well, also what I was going to say about the 2/5 is notice that since they're all going to have the 2/5, we're actually going to factor out that 2/5 to the front. So this is going to be the 2/5 and then the height of the first rectangle plus this 2/5, but we already factored that out to the front, so we just need the height of the second rectangle, which is f of 4/5, which is negative 16 over 25 plus 5. So what's 125 minus 116, or minus 16? Is 109 out of 25. So plus 109 out of 25. Plus the next rectangle, same width that we factored out, but 6/5. So we end up squaring that. It's going to be 36. So what's 125 minus 36? It's 84. No, 89. $89? Yeah, because you'll get 90 plus 35, which is 125. Yeah, so 89. So this is 89 over 25. And then the last one here, 8/5, which is 64. So 125 minus 64, which is 61. So plus 61 over 25. And that will be the underestimate. See how we have the area of all these rectangles. That height was the 121 over 25. This height was the 109 over 25. This height was the 89 over 25 and the 61 over 25. Oh, and then we have one more, the 10 over 25. So that's plus, it's going to be 125 minus 100, so 25 over 25. All right. So now to get that area, we've got to add all of those together. So is there intelligent ways to do that? I suppose, because we could put that onto there. So that's 90 plus 60. So that's 150 out of 25. And then we put this onto there. So that's 110 plus 120. So that's 230 out of 25. So we end up getting 345. No, 380. Yeah, 380 plus 25. So 405 out of 25, which is 16 and 5 out of 25, 16 and 1/5. Whew. All right, so that's the underestimate of this graph. That's the area of these 5 rectangles here. And now we'll get the overestimate. And notice this, that's actually kind of cool, is that like you look at this rectangle here with its width of 2/5 and its height of this. Notice that that rectangle is the same as this first rectangle here. We have all of these rectangles are the same. They're just all kind of shifted over one. So when we calculate the overestimate, it's going to be 2/5 as our width. And then these are all going to be the same. The 121 out of 25 is the first rectangle. Well, it's the second rectangle here. And then the third rectangle here. And then the fourth rectangle here. And then the third rectangle here. I guess the fourth rectangle. The fifth rectangle here. Because that's all, like, yeah. These first four are the same as these right here. What's different is this first one. So instead of having the 25 over 25, this one has 5 as the height. 125 out of 25. Because that's the height of the first rectangle here, but the height of the other rectangles are the same. So now we just have to see what's different. So what I'd like to do is see how this is what it was last time. And notice that this is actually the same. The only two that are different is that instead of having the 25 out of 25, we have 125 out of 25. So that means this one should be 100 more. This should be 505 out of 25, which is 20 and 1/5. So that tells us that the actual area, 16 and 1/5 was an underestimate. 20 and 1/5 was an overestimate. So that means the actual area has to be somewhere between those. Cool. And the whole idea with this that we're about to get into, I bet, is the more rectangles you use, the closer you're going to get to the actual answer. Let's look at what they did. Make sure we got those numbers right. Make sure we just did our math right. We didn't, and we were actually really far off. So we did the same stuff they did. We just added it wrong. They got 162 and 202. Over 5 or over 25? So I didn't write it out like they did, but it should still be right. Hang on. I need to pause the recording and figure out what went wrong here. All right. I found my small problem. I neglected this 2/5. So we have to multiply this by 2/5 and this by 2/5. That's the problem. So what ends up happening then is this can cancel with this and make that an 81. So it ends up being 162 out of 25. And this cancels with this, makes that a 101. So this is 202 out of 25. And so our actual area is somewhere between those. Okay. So don't forget what you're doing. I knew what I was doing. I got caught up in the math. I added all of my heights and got this, but then forgot that then I'd also have to multiply by the width because it was so tedious to add all those heights. Okay. So now we know the actual area is somewhere between those two. Cool. So the next one, we're doing something similar. Find the upper and lower sums for the region bounded by the graph x squared with the x-axis between x equals 0 and x equals 2. So this is weird because they don't tell us how many rectangles to use. We're supposed to find it within rectangles. Okay. This is fun. This is a lot then. So let's sketch out what we've got. They drew some drawings for us, but we should do it without the drawings. So we've got our parabola. So like this. That's a perfect parabola. Oh, no, it's not a perfect parabola. Just needs to go up one. There we go. So there's our parabola. We're looking between 0 and 2. So I guess maybe we could have made it bigger, but we're looking between right here. And we want to come up with a way to write it as a formula. See, we do have to think about the formula here, I guess. But we're going to use the same idea as we did last time. So let's sketch out some rectangles. Let's do the upper bound first this time. And so to see it's the upper bound, see how we're going to go like that and like that. And both of these rectangles go above, as we're including all of this area as well as the whole thing. But it's an overestimate because we're including all of that extra area. But let's build the formula for this. So we've got to think about it. We're doing in sigma. From I equals 1 to I equals n is the base. So we only drew 2 rectangles here, but we're trying to think about it as n rectangles. So what is the width of each rectangle? Because remember how last time we factored that out to the outside? We're going to do that here. So what is the width of each rectangle? Well, the width is 2, that total distance, divided by however many rectangles we have. So you see like here we have 2 rectangles, so the width is 2 divided by 2, so the width is 1. So that's the width of the rectangles. And now we need the heights of all the rectangles, which is what we're adding together. So to get the heights, it's just like last time. We're going to do f of, where of course remember f of x equals x squared. So it's f of Let's take a look at our formulas and let's see. So these formulas, they started at I equals 1. So I would like to start with I equals 1. Right, and that makes sense because that's the first place that we're starting here. So it's 1 width over is the way that I like to think about it. So like each rectangle, you're going over 1 width. So if we think about what we want to plug in, it's a width, 1 width away from the start. So that's why it's like we're plugging in 2 over n. But then for each rectangle, we're going over one more width. So we're multiplying that by I. Because see, then when I equals 2, for the second rectangle, we're adding 2 widths. So in this case, when n equals 2 and I equals 2, that should be 2 times 2 divided by 2. That should be 2, as we're plugging in 2, which makes sense because that's what's right here. So see the anatomy of this. N is how many rectangles. So we have the width of the rectangle, which is the entire distance divided by how many rectangles you have, times the sum of all the heights of the rectangles. Because it's just the sum of the width times the height, but we could factor the width out because it's always the same. The height is different, so it has to stay in. But the height is just plugging in however many widths, I widths, away from the beginning. So that's our formula. Now we need to use what f of x is and see what we can do to simplify this. So we have 2 over n times the sigma of, ends up being 2i over n squared because it's x squared. So then we have this 2 over n to the outside. See, if we do that squared, that's going to be 4i squared over n squared. So the 4 over n squared, we could even bring that out. And this then just ends up being the sum of I squared, which is a formula up here that I don't remember. But that's okay because we can just look them up. N times n plus 1 times 2n plus 1 over 6. So this, now that we're here, this is n times n plus 1 times 2n plus 1 over 6. And all that's multiplied by 2 over n times 4 over n squared. So it's 4n plus 1, 2n plus 1 over 3 n squared as a final answer. How do we feel about that? Not super bad, honestly. I'm not super unhappy with that answer. Let's see what they say here. Did they end up doing different things? They got the 8 over n cubed like I did. Oh, but they got a bunch of these. Oh, whoa, 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 whoa. Why do they have I minus 1? Oh, because they're doing the lower bound. Here's my upper bound. This is what I have. This is what I have. They just went ahead and multiplied it out. I'm not going to multiply it out as of yet. So this is what we have. This is our this is our overestimate that we calculated. Now I want to do the underestimate. I'll do that in purple. So the underestimate is going to be like that. So instead of doing f of 1, you got to start with f of 0. So it's going to be the same idea. I see why it's going to end up being more complicated. I guess it should be slightly different than this one down here. So let's see. We go so the width is still the same. The width is still 2 over n. We're still starting with I equals 1 and we're still going to n. And we're still getting the heights with the same idea of f of the number of widths that we're traveling. But the idea here is the first rectangle, we're not plugging in 1 width away. The first rectangle, we're plugging in 0 widths away. So this has to not just be times I, but times I minus 1. So that's the underestimate, because it's the left side of the rectangles here that we need to touch. So we have to do that minus 1. So let's continue. So just like before, we have the 2 over n, and then wait, this isn't squared. That's just f of 2 over n I minus 1. But that means we're doing 2 over n I minus 1 squared. So we're going to get still the same 4 over n squared. So pull that out to the side. 4 over n squared. But then we have the sum of I minus 1 squared. So I feel like our best bet for that is going to be to FOIL it out. But then we're going to have to separate it. So if you FOIL I minus 1 squared, you're going to have I squared. Oh, geez. We need parentheses here. So we have the I squared. And then this one is going to be a minus 2 that we can pull out. I plus 1, but still in a sigma. So here we have to use all 3 of the sigma notations. So we have, well, there was 4 of them, so I guess just the first 3. So this one, n times n plus 1 times 2n plus 1 over 6 minus 2 n times n plus 1 over 2 plus n. 1 times n. All of that multiplied by 8 over n cubed. Lovely, lovely, lovely. So that's it. I just got to simplify that. So that would involve like 1 fraction on the inside. Ideally, which would also involve canceling out n from all of these and then finding a common denominator. So this is n plus 1 times 2n plus 1 minus 2n plus 1. Except for not 2n plus 1, because I have to multiply that by a 3 to get a common denominator, so 6. All right, because the 2 would also cancel. So minus 6n plus 1 plus 6. All right. All of that times 8 over n squared. So in this case, it is going to be best to FOIL this out a little. So I get 2n squared plus 2n plus n, so plus 3n plus 1, because then minus 6n minus 6 and plus 6. So those are canceling. These are making this minus 3n, so it's 2n squared minus 3n plus 1. But then, of course, all of that times 8. Oh, shoot, it's also all over 6. Right, so all over 6n squared. So that cancels. It just ends up being 4/3. Oh, but there's still the 8 on the top. There's still the 2 on the top. Oh, there's still the 2 on the top of the other one as well. Okay. So I think this is it. I think this is as good as you're going to get. Can you factor this? Oh, you can factor that. Because this is n squared minus 3n plus 2. So that's n minus 1, n minus 2 divided by 2 divided by 2. So this is 2n minus 1 times n minus 1. So that's the underestimate. This is the overestimate. And they're interesting. They're the same, except for this is plus versus minus. Okay. And that makes sense to me, because the whole idea that we're going to go to next is with either one of these, no matter what, once we take this rectangle idea and say that we make an infinite amount of rectangles. So when I drew this, I only did 2. But doesn't it make sense if I were to do an infinite number of rectangles, that area that I'm not getting would get smaller and smaller? And so if there's an infinite number of rectangles, there would be no gaps. So the idea is now if we make n equal to infinity, we should get the exact area. And if we do that with like our horizontal asymptote ideas, look how on the top you have n squared, and on the bottom you have n squared. So the answer is just the coefficients, which is 2 times 4, 8 over 3. So using that formula, we get that the actual area, if we use an infinite number of rectangles, is 8/3. That's using the underestimate. If we use the overestimate, look how it's the same idea, though. We have an n times n squared over n squared, so we just look at the numbers, which is 8 over 3. So that should tell us, I mean, it's really just confirmation that we did it with both of them, that whether we do the underestimate or the overestimate, as n goes to infinity, they both approach 8/3. So that should tell us the actual answer is 8/3, the actual area under the curve. And while we're here, I think they're going to introduce this in a section or two, but that's how the antiderivative applies. If we do the antiderivative of x squared, and we do it from 0 to 2, we should get the 8/3. So let's think, what is the antiderivative of x squared? Well, that's just the reverse power rule. We did that last time. It should be x cubed over 3. And then the whole idea with these antiderivatives, when you have the numbers there, is now we do the first one, we plug it in, 2 cubed over 3, minus 0 cubed over 3. And, wouldn't you know it, that is 8/3, because the antiderivative is a way to find the area under the curves. This is kind of like the slow-mo method before you know integrals. This is another way to do it. You picture the rectangles, and you make infinite rectangles. As the number of rectangles goes to infinity, you see that this formula gets you 8/3. And I think that's a really beautiful thing. So we're trying to do that here. We're trying to go all the way through. So between 0 and 1, it's really like the exact same idea as before. We just have to find one of them, though. We kind of showed that last time, that we don't have to find both. We just have to find one, and we have to make it go to infinity. So it's not going to be perfect now, because it can't draw an x cubed. But let's just do the easier one. So the easier one is going to be the overestimate in this case, right? Because then we're just going to have like the width. So what is it going to be? It's from 0 to 1. So the width is 1. It's going to be divided by n. And then we're going to have the sum of f of, well, I over n, right? However many widths. The widths are 1 over n. So I is which one you're on. Okay. So that's the answer. And then we want to go with the limit as n approaches infinity. So this is the answer. Now we just need to get that answer. So let's see. Well, it's I cubed over n cubed. But just like before, we're going to factor out the n cubed. So this ends up being 1 over n to the 4th of the sum of I cubed. And then you have to come up to the I cubed formula, because you shouldn't have that memorized. N squared times n plus 1 squared over 4. Well, that's not too bad. Maybe you could memorize that. So in this case, that's going to be n squared times n plus 1 squared over 4. That's just what that turns into. And we still have the 1 over n to the 4th. So now you can just cancel. We end up with n plus 1 squared over n squared times 4 over 4n squared. And there we go. And now look at that. As we do the limit, as n approaches infinity, if we plug in infinity for n, see how you're just going to get n squared over 4n squared? So 1/4. So that should be the area as we do this Riemann sum to infinite rectangles with an infinite number of rectangles. Let's test it out real quick like we did last time with our antiderivative. So you take the antiderivative, that's x to the 4th over 4 from 1 to 0. So that's 1/4 minus 0/4, which is 1/4. So beautiful. Obviously, integrals are the way to go because they're shorter and quicker. But integrals are like a shortcut to summations. Integrals really are summations. All right, we got 2 more to do. I think it's just more of just like that. So here we're going in between 1 and 2. So think about with the width, we still got the total distance of 1. So the width of these rectangles is still that width divided by how many rectangles we have. Let's see, do we even need to draw it? Because I'll always think on the right side. So I know this is just going to be F. Well, really, it's just the same as last time, right? To get the height of the rectangles, you're just however many widths over you're going. It's just in this case, the F is a little more complicated. So it's going to be the sigma of 4 minus that squared. So let's see, we'll separate that. And then minus, we got to remember to bring the 1 over n, though, if we're going to separate it like that. So minus 1 over n, yeah, of I squared, right? Or I over n squared. So the over n squared, we're going to pull out to the outside and make that an n cubed. Okay. So then the first one, the formula is just 4n. So this is 4n times 1 over n minus this formula, which let's see, it was n plus 1, 2n plus 1 over 6. So that should be it, right? We just got to go as n goes to infinity. So as n goes to infinity, this is just 4. So that's just going to be 4 as n goes to infinity. And what happens over here as n goes to infinity? So just kind of like expected, we have n cubed on the top and the bottom. So then we look at the coefficients, which is 2 over 6. So 4 minus 2 over 6, or 1/3. So we end up with, well, hang on. This isn't going to be right. Let's finish out. So we ended up with 11/3. But we didn't do it right, did we? Because maybe we do need to draw a picture. Because I think what we just calculated was from 0 to 1. Because the first rectangle that we actually need, well, we can do it 1 over still. But it doesn't start with 0. It starts with 1 plus the width. 1 plus the number of widths. Oh, that's kind of brutal. So what we just did is from 0 to 1. I could confirm that real quick, is if I do this, 4 minus x squared, so you antiderivative, 4x minus x cubed over 3 from 1 to 0. And yeah, see right there is your 4 minus 1/3, and then minus 0 minus 0. So yeah, we just did from 0 to 1, which is not what we wanted to do. So the difference is that instead of starting just 1 width over, it's 1 plus 1 width over. So this is 1 over n sigma. Oh, it's still annoying. It's still the 4. It's still sigma 4 from I equals 1 to n. And then minus, still bring over the 1 over n. But this is the sigma of 1 plus I over n squared. Oh gosh, this is tedious. This is why integrals are so nice. This is so much easier if we did this as an integral. So I guess I should write it out first. 1 plus I over n squared. So what is this going to be? We can start simplifying. So this first one is still 4n over n. But then this is where it's going to go all haywire. So this is 1 over n, the sigma of 1. And again, minus 1 over n, the sigma of I over 2i over n. So I can factor out the 2 over n. So this is 2 over n squared of I. And then plus I squared over n squared. So it's still minus. It's still minus 1 over n. Sigma I squared over n squared. So the n squared is coming to the front. So it's 1 over n cubed sigma I squared. And so now it's just the formulas. Geez. So this is 4. This is 1 over n times n. This is 2 over n squared times n plus 1 over 2. And this is 1 over n cubed times n plus 1 times 2n plus 1 over 6. Man. And now, so this is just tedious. It's really just plugging in a whole bunch of different formulas and making sure you don't make mistakes. And now we plug in n equals infinity and see what happens. So those n's are canceling anyway. We just end up with 3. Here we have n squared over n squared. The coefficients canceled, so the coefficients are just 1. And then we have n cubed over n cubed. So we look at the coefficients, which is 2 over 6, which is 1/3. So this should actually be the answer. 3 minus 1 minus 1/3. Or 2 minus 1/3. Or 5/3. Well, we did it all out, and that's what we got, so it makes sense. Let's do the integral and see if it agrees. So we're doing it from 1 to 2. That's how it's different this time. 4 minus x squared dx. So it's going to be 4x minus x cubed over 3 from 2 to 1. So that's 8 minus 8/3 minus 4 plus 1/3. Okay. So that's 4 minus 7/3, which is 12 minus 7, which is 5/3, which is the same thing we got here. Wow. Yeah, so that's why integrals are so great, using the integral to find these areas rather than these infinite sums. But of course, it's nice to get practice doing it with both. So we got one more grueling one. Oh, but this is just like the same, right? Because we're looking at f of y equals y squared. And the y-axis from 0 to 1. So I guess we can try to rethink it again. I mean, this is just a parabola. It's from 0 to 1. But we're just going to be having all these rectangles just the same. Hang on. Drawing my rectangles wrong. It's supposed to be like this. Wait, let me redraw those. So it's supposed to be, here's one rectangle. There's the rectangle. There's... It's the left side that should hit it. So that's the rectangle. That's the rectangle. Okay, so then what is the widths? I mean, really, I really do just want to say all this is the same as if this were just x. So it's the same as the x squared one that I did. Did I do a plain x squared one? Yeah, it should be the same idea as this. The answer should be 8/3. But let's see. I mean, it's the same idea. Your widths are now this way. That's still going to be 1 over n. I'm still going up for the heights. Of course, the heights are just now sideways. But I'm thinking about at that y value. So it is still finding the x. So it's just going to be I squared, right? Because it's like when you plug in the y value, you've got to square it to get the x value. And that is what it's telling you here. So of I over n squared, the number of widths squared. So that's just like before. You pull out the 1 over n cubed, and then it's just the sum of I squared, which is 2, or n plus 1, 2n plus 1, over 6. So it again... No, we're just ended up with 1/3 here? That's not right. Oh, because this was from 0 to 2. This one's just from 0 to 1. So we just got 1/3. And that makes sense, right? If I just do the integral from 0 to 1 of x squared, you get x to the third over 3 from 1 to 0, which is 1/3 minus 0/3, which is 1/3. Okay. So that was pretty good. And honestly, the next section I think is going to be pretty similar. I think we did everything they wanted to. I'm kind of just confused of how it's laid out in this section a little bit. But that's the idea we're going to reinforce. I mean, it's called Riemann sums. Although 4.3 is actually titled Riemann sums. But that's the idea about a Riemann sum is you divide the area into a whole bunch of tiny little rectangles. And you can find it where the rectangles are above. You can find it where the rectangles are below. But either way, if you make an infinite number of rectangles, that amount that it's wrong should go away. And so if you do as n approaches infinity, then it should be the exact area. And we found that we could do that. Like with this problem, we did the overestimate and the underestimate. And for both of them, when we made n go to infinity, we got 8/3. And then we did the integral, and we showed that we also got 8/3 that way. So I hope that was helpful. Thinking about Riemann sums, thinking about summation. We're going to be doing something similar in the next section.